and your laptop. That's okay. All right, thank you. Great, thank you. It's a pleasure to be here. I'm Kimo Johnson. Did my PhD at Dartmouth College with Hani, and then came down here for a postdoc with Ted. I'm sure many of his PhD students and postdocs have the same experience where you're working on a problem, you show up at the meeting with Ted, you show him his results, and he gives you some great feedback, but then he says, you know, I was thinking about this thing, it's completely different, and then he goes off to tell you something that's a complete tangent, but is incredibly interesting. And GelSight was one of those things. We published this as the retrographic sensor in 2009 at CVPR, and it had this really clever idea of you make this block of clear rubber with a very thin layer of paint on it, elastomeric paint. Anything you press into this, if you look at it through the other side, and then use computer vision, controlled illumination, you can get extremely detailed 3D. And we thought this was really cool. We wrote up the paper and published it. We even made a real-time demo of this. This was a magic box of sorts. You press an object into the gel on the top, had a camera running in real time, and suddenly 3D pops up, and people love this. The responses were incredibly consistent. People will come over and they say, wow, this is extremely cool. Number one question, what is it good for? What can you do with this? And our answer is, we don't know. I mean, this is the great thing about academia, too, is that this didn't come from some funding partner, and it wasn't part of a grant. This was just one of Ted's ideas, and we were working on it just because it was cool. And we continued to refine it with Ted creating the gel in his basement, trying to make it higher and higher resolution. I worked on the illumination, the algorithms, and ultimately, got to the point where we had even higher resolution results. And we published paper at SIGGRAPH and made a YouTube video to go along with it. And that video led to 100,000 views within a couple weeks because they hit the media sites like Slashdot and others, and 1,000 emails in my inbox of people telling me what it was good for and telling me all the things that they could do with it. So this was pretty exciting. And I actually learned something very interesting today, that Ted, you share a birthday with MC Hammer. And if I could go back in time 10 years and tell you something about GelSight, I'd say, Ted, well, MC Hammer was wrong. You can touch this, and this, and this, and these things, and this, and even this. So GelSight technology, it is fundamentally a tactile sensor. You press it up against the surface, but there are an incredible number of applications out in industry where people care about surface quality, they care about defects, for quality control, for inspection, for maintenance, and it really has a tremendous number of applications. So within the company, we've spun this technology out in a variety of different ways. We've made it into commercial products. We have a handheld tactile sensor that's a very high-resolution sensor used by aerospace, automotive, and other industries. As I said, primarily for quality control and other purposes. But then as I was out commercializing this and getting customers, Ted built a whole world around vision-based tactile sensing. And he came back to us with this problem maybe 5 years in. He said, every time I go to a conference and present this, people say, wow, this is really cool. Can we get it? Can we buy it? The tactile sensor version of it for robotics. And he said, I can't sell them things. I can't have my grad students making products. Will you, as the company, start to commercialize it? And that's when we got into making this robotic tactile sensor to help spread the word and get people doing this research. And that ultimately led to a collaboration with our company and a group at Meta with this digit sensor, which is the lowest cost GelSight sensor that's been made. And this is something that we can build and sell for $300. And it really starts to open up the possibilities to get everyone understanding that touch is now possible. Digital touch has become a reality. So commercially, we've focused a lot on the kinds of applications that people saw were possible 10 years ago when we first rolled this out. These were things like industry research groups or companies who make products like I've mentioned. And we've really been able to grow and get this many different places around the world, many huge companies. I'll give you a couple ideas of typical applications. So the most common application right now is in aerospace. And you wouldn't believe this, but when you fly on a plane, there's only about a quarter inch of metal between you and the outside world. So they care a lot if there's a scratch or a dent on the outside of that surface. They care for a couple reasons. One is if it's too deep, potentially it becomes a crack. It can affect the integrity of the aircraft. But two, with all of those little surface imperfections, fasteners in particular, there's 350,000 fasteners on a Boeing 737. If they are out of flush, then the accumulation of effects can affect fuel efficiency. So they really care about even the smallest little detail on this gigantic aircraft, but they have primitive tools for dealing with this. It's surprising, but I heard countless stories at many different companies of, well, we just feel it with our fingernail and decide if it's in or out of spec. And oh, the guy over in that other team, he's more sensitive. We'll get that guy to come over and feel it with his fingernail. So I mean, this is the reality in many different places of how people will do this. With our tool, they can go up as soon as they see an issue, press the probe in, and within a couple seconds, they can get a digital representation, and an answer is this in or out of spec. So there's a lot of value, and that's what really drove adoption of this technology. Common measurements, as I said, scratches, fasteners, measuring welds, things that I wouldn't know were problems, but people came forward and found our technology and told us this was a great match to these problems. But closer to what TED has been doing with vision-based tactile sensing, we've started to work with collaborations with companies like Magna, where they explain their problem of they have many factories around the world. They're a big automotive supplier. And finding people to work in these factories is a big problem now, especially with the pandemic and others. They're interested in automating a lot of tasks that people are doing with their hands today. It's not so much about being more efficient than a human. It's about making sure that you can have exciting jobs for the next generation of students, people who are graduating. It's not that interesting to many to go into manufacturing. So how can you, instead of doing the task yourself, train a robot to do a lot of tasks people are doing with their hands today? This task shown here happens to be just simply picking up a part from a bin and placing it on a fixture. But this can be hard in some cases. This happens to be a gear, and they want to put it on an axial line fixture. What's been fascinating, though, is to learn about these problems that are still being done by people today and that are very manual, whether it's visual inspection or tactile inspection. And I have a couple examples of this as well, where this comes from an automotive supplier. They have incoming materials, and they just have industrial designers or people who have decided these materials are good, they're acceptable, these are not. They ask people to learn the difference, and then people just have to make these judgments. In this case, there are 3 different types of wood textures that were going into a fancy electric truck, and they liked certain ones, they didn't like others. And we showed that, look, this is very easy to classify by measuring them with our system and training a model to learn the labels, essentially. This exact same process we found at a supplier to the EV industry who's making wires for batteries. And they had this one woman, her name is Jules. She would sit down and look at those wire rods under a microscope and say, this one has surface defect number 3, this one has a subsurface defect number 5. And she just knew. But it's hard to really fully understand all the distinctions. What we were able to do is train a model on measurements with our system and the labels that she provided and get extremely good matches to her. So essentially, we've made the virtual jewels that can then be deployed to all their factories, and they can use this, and that solves one of their key problems, which was disagreements from the main plant versus the others on the grading of these different parts. So this leads me to the bigger vision for this technology, which is look at all the places where human hands are still being used in manufacturing, in part of things, our lives. Like human hands are still packing the boxes that you get when you order something from Amazon. Human hands are still assembling products like the iPhone or inspecting airplanes. And how can we start to digitize and represent what the human hands are feeling? And when you think about it this way, it's a big opportunity. There's a lot of money and a lot of time being spent on inspections. There's a lot of money being spent on human hands to do tasks. And this is where, as a startup, we start to get excited. Like we can start to chip away at some of these problems and offer automated solutions that are more reliable and more available than people in many opportunities. So inspections being one that we're already doing today. But assemblies, things that are being assembled by human hands, can we start to train robots with robotic touch to do them? So we started out with just a few of us. I happened to be able to dig up this picture. It is a digital photo, but somehow it still looks very dated. I don't know how that happens, but it is the case that we're still having a lot of fun today. We've gone from 4 there to 27 and having a lot of fun getting this technology out into the world. Thank you.
Thanks, Kimo. Questions?
Yes.
Do you have competition?
There's always competition, yep. I think actually what we found over the years, though, is that the most challenging aspect about this particular company is the fact that the opportunities are so broad, and we can go in so many directions, that it's hard to figure out which is going to be the area to focus the most. So we've been able to find customers in aerospace and automotive, in a variety of places, but each of them have different needs, and that's probably been more challenging than having to worry about competitors. Yep. Yes?
So to get those fine details, this material must be very deformable. But for force estimate, bottom out pretty quickly.
Yes, I suppose you can. It just depends on the range and the limits. This is something where, in fact, we've had to adapt the applications, or at least filter the applications by the capabilities or limitations of the sensor itself. So, I kind of joke to say, you can touch this. There were certainly a variety of applications, semiconductor and others, where people do not want contact. They do not want our sensor touching their parts. And I think similarly, if you're doing force estimation, there's a range in which this sensor would be applicable and probably a range where it's not. So, it has also been a filtering process to see what are the good matches to what we can do. Thank you.